All right, this is, first of all, it's great to be back at Flash Memory Summit. You know, a lot of us, the industry vets, like coming to this event, seeing all of our old friends, seeing where everybody's at. It's been a couple years. So anyways, thanks for coming into this session here. What I'm going to go through today is new technology that's been in development for several years called SoftwareEnabled Flash. And this is an open source project that Kioxia is leading. And I'm going to go through the initial top level overview of the project. And then my co-partner here, Earl, is going to go over the more technical side of the aspects. And then we'll be around afterwards if you guys have any other additional questions or discussions. And again, we're from Kioxia. We're just the lead on the project. But again, this is an open source project where you'll start seeing more vendors and other participants and other customers make announcements on it as well. So today I'm going to go through the development, the different capabilities of software-enabled Flash, and a little bit about the open source platform. Some of you are probably familiar with Linux Foundation and that technology, but I'm going to give a quick overview on that. And then Earl will take it over and go over the hardware side of things, which is going to be delivered by Kioxia first, but there'll be other vendors as well. And a little bit more about the software. And then we'll close with a little bit about joining the project, which is open to everybody. So how did we get here? So the initial development of this whole software-enabled Flash project was brought up by discussions with Hyperscale customers. That's the largest deployment of Flash media globally, and they really needed the ability to take advantage and squeeze every bit out of all of the Flash media. So starting back in 2018, again talking with these Hyperscale customers, finding the pain points, finding how we can really take advantage of all the capabilities of Flash. So we started to build a simulator to show the capabilities, and then the first hardware designs with the FPGA platform. And then last year, we published the first API, the first software code part of it. And then this year is a really big transition year for us. This is where we're starting to bring the ideas to market. So the beginning of this year, we officially launched the open source project under the Linux Foundation. So it's now, again, an open source project, so anybody can participate at various levels. And then the hardware development will be by individual manufacturers that want to take advantage of certain parts of the platform. But the main thing as we go through this, to think of software-enabled Flash as an umbrella to do a lot of software-defined capabilities under Flash. So we already know a lot about software-defined. There's a lot of software-defined storage platforms, software-defined networking, where basically the developers can tweak the applications to do whatever you need at that particular time with the hardware. But until now, Flash wasn't really taking advantage of being software-defined. It was just stuck underneath the legacy HDD protocol. And so with software-enabled Flash, it is now software-defined. So that's really the key takeaway on this technology, is making Flash storage software-defined. So when you hear software-enabled Flash, what we're saying, that's the brand name, but the capability is making Flash for the first time fully software-defined. And we're moving all of the legacy HDD interface or protocol barriers that Flash has been underneath. And everybody knows that Flash has a lot more capabilities. If you can get down to the cell level, you can do a lot more with Flash than what the legacy HDD protocols employed. And what this also allows us to do with the software-enabled Flash API layer, we can move applications forward on new technologies. You know, we all know about TLC and QLC and all the next generations of Flash that are coming out from both Kioxia as well as other vendors. And what this software-enabled Flash layer allows you to do is move that application to the next generation of Flash without having to rewrite your application. So this allows the cloud environment to really move forward with the next generation technology, again, without having to take down or rewrite their applications. And Earl's going to go a little bit more detail on that. But basically, this is a software-defined Flash API, the software layer that just sheds this HDD paradigm that's really kind of constrained the capabilities of Flash that's always been there. So now Flash can behave in a much more predictable manner, and with the same hardware device, you can modify it depending on whatever your application is at that time or whatever your requirements are without having to change out hardware or to change out your application. And this allows you to give latency control or whatever read-write priorities you need at any given time, or delay garbage collection, any type of parameter with Flash specifically that you never saw on a hard drive, so that it wasn't in the legacy protocols of hard drive. And this allows the multi-protocol capabilities to really be unlocked inside of Flash hardware. So this software-enabled Flash technology, by making Flash software-defined, is really what we call a force multiplier in data center economics. So now you can deploy one SKU however many millions of times you need it globally in the data center, but then you can change the environment, and whether it's an isolated tenant environment or you want to deliver different levels of service, maybe you have different campaigns going at any given time on that server. And again, it's the better economics because you can use one SKU, but modify it with the application layer, with the API layer under software-enabled Flash to tweak that one SKU, again, millions of times, to do very different things underneath the software-enabled Flash technology. So this, again, gives you a better TCO on that drive. Faster time to market because, again, now you can deploy new drives, the new generations of Flash hardware, without having to rewrite your applications to take advantage of those. This is all going to be done in the software-enabled Flash API layer. And the other good part about this is it's an the software-enabled Flash API is open source through the Linux Foundation. So any manufacturer can develop the hardware to support this environment. So again, this project is live. The open source project on the Linux Foundation is live, and anybody is welcome to participate, to follow us at the website. We'll show at the end as well, but softwareenabledflash.org, very simple. And we have a lot of different ways to get involved. There's a governing board and a technical steering committee that drives the core development of the project, as well as an outreach committee that's doing all of the evangelizing and the project development. And then there's different various project communities, because again, as I said at the beginning, the software-enabled Flash, you have to think of it as an umbrella. It has a lot of capabilities to do various things with Flash technology. So there's going to be a lot of sub-projects underneath it. So what we're trying to do is combine the best of the Linux Foundation and working on the best practices for this open source project. So again, there's a lot of ways for people to get involved, and it's open to everybody. softwareenabledflash.org. Again, it's a vendor neutral. You'll hear a lot about it from Kioxia because we're the founding member, but as we go forward through this year, you're going to start seeing a lot more of this logo, as well as other vendors talking about it, other customers and other what we call co-travelers, other participants and developers that are involved in this project. So you'll remember, you heard it here first. We've been working on it for 4 years, but this is when it's really finally starting to come to market. And again, we encourage everybody to just go to this website, take a look at it, and anybody that's involved in any data center platform with Flash technology, I think you're going to find this is very interesting to really finally take advantage of the real power and just unlock the capabilities of Flash and just kind of break free from the hard drive legacy constraints. And so now I'm going to introduce Earl. He's going to go through, he's on the technical marketing side as well. So he's going to go through a little bit more detail on the hardware. So now we're transitioning from the public platform with the open source software side to the actual hardware that's going to be delivered initially first from Kioxia, but you're going to hear about it from other vendors as well. So Earl, you want to take it away there?
Awesome. Thank you, Sean. Thank you, everybody. So Sean went over kind of the why you'd be interested in this and why you should be interested in looking at it. I'm going to double click a little into it and talk about what the really cool features are that make it different from maybe anything you've seen that's going to enable a lot of the power, a lot of the flexibility we're talking about bringing into Flash for hyperscale and for data center use. So we're going to talk first about the hardware. We're going to talk about the different components of the hardware, how they work together to provide a new way of thinking about Flash, making it software defined. Software-enabled Flash is built on two things, really, two very different pillars and two very important pillars. Optimized hardware that's built for software-enabled Flash. that takes care of the low-level flash management. Things like flash programming, things like erase times, all of the very vendor-specific, process-specific issues that really give headaches to other people trying to use a flash. That's what the hardware takes care of. On top of that, we provide an open source software layer. And this is what the open source software-enabled Flash organization is all about. That allows that power and that hardware to up-level, to be able to be used inside applications, where you can define things like protocols, latencies, isolation, etc. I'll go into the details as we go through here. So the first and most important and simplest way the software-enabled Flash is different is the hardware supports hardware-based isolation. And this allows applications of the data center, orchestration, to actually define different domains. It's very much like an NVMe endurance group, where workloads are completely physically separated, so they cannot interfere with each other. So it's very easy to keep different SLAs, different priorities in different spots of the flash with this. On top of this very gross die-level hardware isolation, we have something called quality of service domains. These are a higher level of abstraction that allow the software to partition these individual hardware domains into even further isolated groups. The way to think about it is a quality of service domain is, say, a workload. This is going to be a database file. This is going to be the ephemeral storage for a virtual machine, something of that sort. And the idea here is using these quality of service domains and a lot of the underlying technology, we're able to isolate dynamically and let the orchestration software, let the upper layer levels of your storage stack define the isolation, the latency, the prioritization between different workloads. We do that through the quality of service domains. What the quality service domains provide at the various highest level is data placement control and data placement isolation. The idea here is different workloads really want to keep their data separated in the cloud or in different storage devices that have very different needs. You don't want to mix workloads data in an individual flash superblock, because that can actually end up affecting the performance of your neighbor's workload. The idea here is with quality of service domains, you actually are able to isolate inside the device. You can tell it to isolate, keep all of this application's data in one set of superblocks. Keep all of that application data in a different set, and never the twain shall meet. What that allows is actually a very neat feature later on, especially in virtualized environments where these tenants come and go on a millisecond basis, is because the data is isolated between tenants, between quality service domains. You can actually reclaim the data for deleted domains instantly. There's no garbage collection required. This reduces write amplification, which is going to extend the life of your device. This is going to improve the performance because you're not wasting time reading and writing back data inside this, what I used to call the I/O blender when I was looking at, standard drives. You're not going to see that effect here because everybody is still isolated. And if we go even further, inside these quality of service domains, we support a really powerful, really unique queuing structure. IOs can be prioritized between quality of service domains, both at creation and dynamically as things progress. If you're an e-commerce site and all of a sudden the web tier needs to get better priority than your database backup, that can be adjusted on the fly using either simple priority based, we have a round robin so everybody gets their fair share, or we provide something that's actually really unique called die time weighted fair queuing. And this lets you assign for every quality service domain a weight for every type of operation, whether it's a read operation, a write, or say a flash erase. And by doing so, you're able to, if you had, for example, a desire to say 50% of my time on the die I want to be writing, and 50% I want to be reading. You can actually adjust priorities to make that happen. If you want to lower the priority of a backup job because somebody else is coming in and they're paying more for that time, that is also possible here by adjusting these weights. They're per quality service domain, and they're dynamic, which is really awesome. When we look beyond that, we talked a little bit about garbage collection. Well, garbage collection here in the software-enabled Flash domain, software-enabled Flash technology domain, is handled kind of in a unique way. Now, you are managing the Flash at your application layer with SEF. In typical devices, if you were going to do a garbage collection operation, what you do is you read the valid blocks of data from the Flash into your host DRAM, you assemble, and then you write it back to a new pre-cleaned area. This is really wasteful, right? You're wasting all the power and bandwidth over your PCIe, you're wasting your host memory, etc. Software-enabled Flash has in-drive hardware supported copy offload capability. And what that means is a single command here, which if you can spot the incorrect digit in pi, I don't know, I'll give you a t-shirt. The single command here can actually have the drive perform the collection right in the drive and do that operation in a very powerful way. We support both bitmap based as well as what we call ADUs, but most people call, it's essentially LBA sectors. And this power is built into the drive and part of the software stack automatically. Speaking of that, and this goes back to what Sean was talking about. Before, if you really wanted to get low-level access to the Flash control, you had to know how to program the Flash. You had to know every vendor's version of every chip, all the timing specs, all the quirks, etc. Because software-enabled Flash is built at a higher level, the hardware is taking care of that. It's abstracted. It makes your software much easier to port to new technologies. It makes it much easier to port between, even different Flash vendors. This is an open source vendor neutral collaboration, obviously. And that is great. I mean, that helps with your time to market. That helps you explore different options in the marketplace as well. As newer technologies come along with better economics, you can deploy them faster with this kind of technology. Again, because the hardware worries about the Flash details. You at the application, you at the hyperscale, you at the storage stack worry about the best way to organize your data. That's the way to think about it. So that's kind of the capabilities in the drive, what we call a SEF unit. On top of that, and this is really neat, and this is something that I haven't seen in a lot of storage devices or storage organizations. This is a really detailed software stack that's above it. I'm going to talk about the API and the SDK that are available or will be very soon available that allow you to take these drives from whatever vendor and do some really cool stuff without a lot of work. So initially, software-enabled Flash, it's based off of an NVMe command set, but you don't have to speak NVMe. We have a low-level API that's basically a library. It's shared or dynamic. Source code is obviously fully provided. We're an OSS, Linux Foundation setup. And basically, you get low-level access to the drive through a C binding or C++ binding or Rust binding. You don't have to worry about low-level kernel details and low-level register maps. Above that, because this is really low-level, this basically, at the end of the day, it exposes the 4 or 5 special commands that SEF enables. At the end of the day, we expect a lot of people will be using a higher level SDK. This software development kit, it's going to be released later this year, and it's going to provide 4 major components, all source code provided. Again, open source. Command line interface that allows the orchestration, the management of the life cycle, things like creating those hardware isolation domains or those software quality of service domains I talked about earlier. From the command line or through your orchestration software. It's actually scriptable. There's a little Python interpreter included. Everybody knows Jan Zaxbo's FIO tester. I bet everybody here has used it at one time or other. We've actually built a storage engine that supports our SoftwareEnabled Flash API that runs under FIO. Now, with that, that allows you as an end user to do simple benchmarking, simple exploration of, hey, what happens if I adjust my knobs for my queuing in one way or another, or if I adjust my isolation parameters. Beyond that, at a higher level, we provide basically a zero-code way of trying SoftwareEnabled Flash in your own application through reference virtual device drivers. So these are VirtIO drivers for QEMU that support an emulated block device, just like everybody's used to, an emulated NVMe device, or even an emulated ZNS device. QEMU, the guests get this emulated ZNS, etc. QEMU using this device driver actually talks directly to the Ceph device using Ceph commands to make that happen under the scenes. And with that, you can also adjust your timing parameters, your queuing weights I was talking about, the isolation. All that's workable with these in this virtual domain. And finally, we also support something that's really cool, the reference flash translation layer. This is a complete FTL, including garbage collection and recovery from power loss. You name it, it's there. It's not intended to be the be-all and end-all of FTLs, and we expect people will take it and run with it and build better FTLs that better suit their needs. But the idea is it provides a very simple plug-and-play way of taking an application that likes block and running it under SEF. And then because this SDK, this FTL is modular, you can actually adjust things like swapping out the garbage collection algorithms. You could adjust the way the timing is done, etc., all in source code. Again, this is all source code provided. The idea here is this software development kit gets you out of the door, gets you using SoftwareEnabled Flash faster in your applications, doing prototypes, etc. Well, you can take that, you take the source code, and build your own applications with it afterwards. So, talking about that, and I talked a little bit about this with the virtual side, SoftwareEnabled Flash also with the SDK provides some really cool capabilities that I don't think I've seen in other storage technologies. Because the API, the way your application talks to the Flash, is all software controlled by software, you guys, right? You can take one physical drive, one Ceph unit, and it can be deployed as a standard block device, using a standard block, the reference FTL driver, for example. It can be deployed, that same unit that was block device can be redeployed or deployed from scratch as a ZNS device or as, say, an object device, whatever you decide. The key here is, thanks to these little device drivers that are living in your application that map from the protocol that's best for your app to SEF, you're able to simplify your SKU management. You're able to keep fewer device types on hand and get the same flexibility, and in fact, a lot more flexibility, because you're able to actually define how you want to use a flash at a much lower level. So we're open source. We have a booth. We have some really cool demos. If you want to stop by, we are in the Kioxia booth right at the entrance. We have SoftwareEnabled Flash has a kiosk there where we can talk to you and show you some of the demos demonstrating the workload isolation, the multiple protocols, etc. So stop by, check our website out, softwareEnabledFlash.org. Join the program. It's Linux Foundation. We are vendor neutral. We want to get the community involved, get your feedback, get your intelligence working to make Flash better for everyone. So with that, thank you all for your time, and thank the NVMe org for having us here.